In this video, we will learn about truss analysis using method of sections, topic 6.4. The method of sections. Objective is to calculate forces in truss members using the method of sections. Now, method of joints is very easy to use, where we can just draw the free body diagram for each joint and solve for the forces within the members connected to that joint, and then move on to the next joint and solve for the forces, and then move on to the next joint and solve for the forces. Now, for example, in this bridge, if we are interested to calculate the forces within these three members here, then we cannot solve them directly by drawing free body diagram for this joint, but we have to start solving from outside to inside. That is what method of joints do. So in method of joints, we start with this joint, solve for these two members, then move here, solve for this and this, then move here, and then solve for the remaining members, and so on. So this method is easy, but it's time consuming. That if you are interested to calculate forces within only certain members which are embedded inside of the truss, not more on the external side, such as here and here, then we have to solve all the joints in order to reach those members. To overcome this limitation of method of joints, the method of sections is being invented, in which we can take the cross section. We assume using imaginary plane, we cut the truss into half, passing through this particular three members, and then we remove one of the sides of the truss and then expose the forces within the members of the truss, and then solve for them directly without solving the joints which are along the way. So it's much more quicker to use method of sections to solve for the forces in certain members only. So say for example here, if we would like to know the forces within the member GC, we cannot draw a free body diagram for G because we need to know all the forces in the members which are connected to G. So we have to start from here and reach all the way up to G, or start from here and reach all the way up to G, and then draw the free body diagram for joint G and solve for this member. However, if you use method of sections, we can directly solve for that force. In method of sections, generally a cut passes through no more than blank members in which the forces are unknown, and the answer is 3. If a simple truss member carries a tensile force of T along its length, then the internal force in the member is also tensile with magnitude of T. So the correct answer is D. Okay, a few examples here. Applications. Long trusses are often used to construct large cranes and large electrical transmission towers. The method of joint requires that many joints be analyzed before we can determine the forces in the middle of a large truss. So another method to determine those forces is helpful, and that's called the method of joints. Method of sections. In the method of sections, a truss is divided into two parts by taking an imaginary cut, as shown here by AA. It doesn't have to be a straight line. It can be like any geometry in 2D through the truss. And since the truss members are subjected to only tensile or compressive forces along their length, the internal forces at the cut members also will be either tension or compression with the same magnitude as the forces at joint. And this result is based on the equation equilibrium principle and Newton's third law. So let's say this is the member which is in tension. So when we take this imaginary cut, we split that member into two. So the internal forces within the member is now exposed, but that internal force is same as the external loading here, so and in the same direction. So if this is pulling here at this new internal joint, the force is also pulling at the joint, and same applies to the other half. Similar to that, if a member is in compression and we cut it and split that into two, then both these sections are also in compression. So what we do here is we take the cross section, we expose the internal forces, and we have considered the left. So once we take the section at AA, we have a freedom to select either only the left side of the section or right side of the section. So in this example, we have selected the left side and exposed the internal forces FBC, FGC, and FGF. Looking at the arrows, we are assuming that this member FBC and FGC are in tension, and FGF is in compression because it is going inside the member. So for method of section, if the arrow is leaving the member, that means we are assuming that the member is in tension. If the arrow is going inside the member, that means the member is in compression. And this is the left side and this is the right side of this section. We can select one of those sides and solve for the unknowns. We may need to determine the support reactions before we apply any other equation of equilibrium, but here we have freedom to apply three equations of equilibrium, that is sum of the forces in x equal to 0, sum of the forces in y direction equal to 0, and sum of the moments equal to 0. But we apply those equations to the entire half section of the truss, not at individual joints. We consider this loads as now external load and solve for the forces within these three members. Okay, so that same method is being explained here. And then we apply equations of equilibrium to solve for the unknown forces. So let's look at this example. Uh, this truss is subjected to three external loads such as 20, 30, and 40 kilonewton at B, C, and D. We need to calculate the forces within the member Kj, which is here, Kd, which is this, and Cd, which is here. Now we can take the cross section as a, or the imaginary section as a straight line going through those three members. Okay, so we take this imaginary cut passing through those three members, and then before that we need to calculate the support reaction. So we will calculate the support reactions at A or G. Okay, so these are our support reaction AX, AY, and GY by considering this load and the support reaction forces. And then the next step is take the cross section and we keep the left side of that cross section and remove the right side. And we expose the internal members, and for each member the arrow is leaving the member. That means we are assuming that all three members are in tension. Now for on the left side of the section include all the external load and support reactions that are applicable. So 1, 2, and 3. So this is support reaction and these two are externally applied load, and these are our exposed member. So now consider this and new diagram as our problem with three unknowns, and we have three equations of equilibrium, so we can solve for three unknowns using those equations. Okay, and that's how the problem is being solved, and we will actually solve the problem in the next video. Thank you.